Welcome to Fun with Science and Engineering Technology. My assistants this morning are Catherine and Melissa. And what we're going to discuss today are the engineering design process and also the Universal Systems Model. We'll start off with the engineering design process. This is a design process that all engineers go through when they're designing something. For instance, my ballpoint pen, right, goes through the same process. If you're designing a car, it goes through the same process. If it's a guided missile or a space shuttle, everything goes through basically the same process. So it's an 8-step process. And Melissa, what's the first step?
Identify the need or problem.
Right. So the first step is to identify the need of the problem. Right. Usually, if you're working as an engineer, you're probably going to be working for a large company, and either the customer for that company or the company president or so forth is going to say, hey, this is what I want you to design for me. And let's take, as an example, let's take an automobile that's going to get us 50 miles to a gallon and travel at 100 miles an hour. Right? So after we get our problem that we're going to solve, which is what engineers do, they solve problems, what are we going to do next?
Research.
We're going to do some research. What do you mean by research? We're going to study the problem, right? We're going to take a look at all the things that have been done in the past, right? Take some look at some new technology maybe, and decide what we're going to do, right? Our research, maybe what we want to do is we want to look at some different cars. We have a car like that, right? And then we have another one, which is a track vehicle. It's got, instead of having wheels on it, right, it's got a little track. And then we could possibly look at something called a hovercraft. You know what a hovercraft is? Right? If we were to take this, I have a little hovercraft, right, which is a CD-ROM, right, and a balloon and a spool. And if I blow the balloon up, what happens is the air comes out of the bottom, and there's a little cushion of air that this will ride on. We're not going to do that just right now. We'll save that for later. But so I take a look at what everybody else has done. Right? One of the goals that I have, one problem I have to solve is I want my car to get 50 miles to a gallon. Right? This Jeep kind of a vehicle, right, is one possibility. It has wheels underneath it, right, allows it to run. Or I have this vehicle here which has little tracks. Right? Those are pretty good because they got a lot of contact with the road and a lot of friction, so they have a lot of traction. This one over here, right, is going to ride on a cushion of air. So what happens to the friction there? Which one has the least friction?
The hovercraft.
This hovercraft, all right, that's going to ride on a cushion of air. So my goal is 50 miles to a gallon, so what I want to do is get the friction as low as possible, right? So this would be my best bet to reduce friction, is this hovercraft. The only problem with the hovercraft is, like, if it runs over here and it runs over that hole, the air leaks out from underneath it and it goes down on the ground, stops. Or if I wanted it to climb up a hill like this, right, it starts to climb up the hill, and what happens is the space here gets big and the air is going to leak out from underneath it, and it's not going to work, right? We'd have to turn it into a helicopter in that case. So that's not a very good solution for a car that we're going to drive down the road. Okay? If we were to take that hovercraft, guess what would happen? We have a green bridge over here, the duck bridge, that green bridge. Mm-hmm. What about that bridge? It has holes in it, right? It's a mesh. The roadway is mesh. So if we had a hovercraft, we're going down to go across that green bridge. What was going to happen to the cushion of air that's underneath it? It's going to go away. It's going to go down through the bridge, right, down on the Merrimack River, and the hovercraft's going to come down and sort of stop right there. So that's not a very good solution. So when we're doing our research, we come up with all these different ideas, and we're going to come up with 1 or 2 or 3 solutions, right? Which is the next step, right? What is the next step?
Develop possible solutions.
Develop the possible solutions. So that's what we've been doing, right? We've decided this is really not a very good idea, right? This one, right, like a standard car, it's got wheels underneath it, and with the bearings and so forth, and the grease, all the lubricants, the friction is reduced pretty low. This one over here, right, the wheels on the ground, right, those track vehicles can't run very fast, right? We want to do 50 miles, 100 miles an hour. So this is not a very good solution. Right? So we take a look at it and we say, okay, well, last week when we were doing the aircraft thing, we were talking about drag, right, which is the force that holds the airplane back when it's flying through the air. We had thrust, which makes it move forward, and then the drag, which holds it back. Well, this vehicle here, being square shaped like that, is going to have a lot of drag. It's going to have a lot of resistance as it goes through the air. Right? This one over here, though, is all streamlined. Right? So maybe in our solution, what do you think we might do? Do we want to use this one or use this one? What do we want to do?
Use that one. Use that
You want to use that one? Why?
Because it can go faster.
It can go faster, right? But I got a lot of drag. I got a lot of force. When the air comes up over the top of this, there's like a little vacuum that forms in the back of it, which is going to hold it back. I want this thing to be able to do 100 mile an hour. And plus the fact that that drags it back, it's going to cause it to use more fuel. That drag's going to make it use more fuel. This one is streamlined, so the air flows over the top nice and easy. Right? But what's the problem with this one?
It can't go fast.
It can't go fast because of the tracks, right? But so what am I going to do? My engineering team, right? What are we going to do? You had a solution?
No.
Do I have to use this one or this one?
No.
No. Can I use a combination of the two? Would
Yeah.
that be a good idea?
Yeah.
Okay. What are you going to do? What are we going to do now?
Put wheels on this one.
Put wheels on this one. In other words, take the wheels off of this one, put it over here. So your design that we've arrived at, right, is we've took 3 possibilities that we had, and we come up with a compromise. Right? Catherine may have liked this one. Right? I like this one, and you probably like this pretty blue one, right, Melissa? So, but what we did is we do exactly what the engineers do. We sit around the table, we all had these different ideas, and we came up with one design we're going to try to build, right? And it was a compromise. Basically, we all worked together and we come up with a compromise. So, our compromise was take this body, put wheels underneath it, right? Because the wheels have less friction than the tracks, and the aerodynamic shape of the body gives us less drag, so we can come closer to getting our 50 miles a gallon at 100 mile an hour. Yeah, so what's the next step? What are we going to do next? Now we come up with a
Select the best possible solution.
okay, we've done that, right?
Construct a prototype.
Construct a prototype. What's a prototype?
A sample.
A sample, right? It's a model. And usually, right, it's a full-size working model. Okay? We're going to put it all together. You're going to take this body, we're going to take these wheels, put it on that body, we're going to construct a prototype. A model. So, and why do you think we're going to build a model?
Test it.
Do what?
To test it.
To test it, which is the next step. Right? We need it. How we build this thing, we design it. All right? We did our best job we can designing it, but we don't know if it's going to get 50 miles a gallon, and we don't know that it's going to do 100 miles an hour. You may get 50 miles a gallon, do 100 miles an hour, and fall apart. That wouldn't be good either, would it?
No.
No. All right, so we're going to test. So our next step is to do what?
Test and evaluate it.
Test and evaluate it. So after we get the prototype built, we're going to do test and evaluation. How are we going to test and evaluate it?
Make it go 50 miles an hour.
We're going to take it out, and we're
100
going to
miles.
drive it, right? We're going to drive it. We're going to drive it at 100 miles an hour and see if it gets 50 miles a gallon. Well, how long are we going to do that for? An hour?
Until you're positive it works.
Until you think it works, right? And until you collect enough data that you think it's really going to do it. All right, and the reason you need to collect this data is because the next step is to do what?
Communicate the solution.
Communicate the solution. We've got a car, right? We've collected all the data. Now we're going to go into the boss, right? The president of whatever car company this is, XYZ car company. And we're going to say, President, sir, we've got the car you wanted. Right? We've got a car that we've tested, and it does 50 miles to a gallon. You can drive it at 100 miles an hour. Right, and here's all the test results. We drove it for 3,000 hours or whatever it is, and we drove it over all kinds of roads, right? And we used all different kinds of fuel, and we ended up with these test results, and we know it does this. All right, so we try to explain to him, all right, how do we know this is all going to work, and how is he going to build it? Right? And we say, well, gee, boss, now it's time you got to fess up, right? We say, well, you know, to get 50 miles to the gallon, we got to build a special engine right in here. We have to have some special materials, and these materials there's only just a little bit of it, right? And we're going to have to go to the moon to get some more. And he looks at us and he says, okay, how much is this all going to cost me? Well, we figured, you know, if you build 10,000 cars, they're going to cost you $100,000 each to build. What's he going to tell me?
No.
He's going to tell you, no, right. He's going to say, hey, hold it. I can't, you know, sell a car that's going to cost me $100,000 to build, right? Even though it does all those good things that you said it was going to do. It goes 100 miles an hour, gets 50 miles a gallon, and besides that, I can't get any materials from the moon, right? So what's he going to tell you to do? He's going to tell you to go back to the drawing board and do the next step.
Redesign.
Redesign. So a little tear in our eyes. We leave the conference room, we go back to our desk, and we sit down and say, okay, what are we going to do now? Right, and we do some redesign. Right? And we take another look at the problem. And guess what happens then? The next thing that happens is we go right through this whole loop again. We can do all of our redesign, we do some more research and analysis and so forth, and we get down here, we build another prototype, or modify the prototype that we have, and go through the whole sequence again and change it. Okay? So now then we go back to him and we say, okay, boss, here we have a car that does 100 miles an hour and it gets 50 miles to the gallon, and it's only going to cost you $2,000 to build. And he says, hooray, we're going to build 100,000 of these and make lots of money because I want to sell them for 15, 20,000. Right? So I'm going to make a lot of money on this car. So, now, that goes on, and we get all these cars out on the road, and something goes wrong. The left wheel keeps falling off of them. Even though we did all our good design, and we did all of our testing and everything, there was a little flaw in the materials that we used to hold that left wheel on, and the left wheel keeps falling off. What's going to happen next?
Gotta redesign.
We're going to have to, if people out there are going to start complaining, we're going to have to go through a redesign. Right, so we have to start with our redesign. Right, and we go on and on and on, right? How long do you think this whole process is going to take, going to last?
A long time.
A long time. Let's look at the next picture for a moment. Can you see that? What is that?
A car.
It's a car. What year is that car?
1908.
It's a 1908 Oldsmobile. I picked the 1908 Oldsmobile because they just quit making Oldsmobiles after 106 years. Last week they stopped. The last Oldsmobile was built. So here we have one that was 1908. Can you describe it a little bit?
The wheels are big.
The wheels are big.
Yeah. Not a very good roof or windows.
Does that have windshield wipers?
Nope.
No,
Why? Why doesn't it have any windshield wipers?
because
Because
it doesn't have a crystal or something.
It doesn't have a
Yeah.
windshield, right? So you
Yeah.
don't have any need for windshield wipers. Does it have headlights?
yeah.
Little headlights. And if you look real careful, it also has some tail lights. It has 4 wheels, just like the car we just designed has 4 wheels. Right? So it doesn't look like an automobile now. It doesn't look like that last one they built last week, right?
No, it's different.
But for 106 years, this car has been going through this design process. Every so often, it goes through that whole series again and gets changed. Over and over and over and over and over. Now, you think that was all done by just one person?
No.
Even the last model that they just built, there was a whole bunch of different kinds of engineers. Right? My ballpoint pen, right? Do you think it was designed by just one person?
No.
No.
You think there was a team of people?
Yeah.
How many different kinds of people do you think it took to design this very simple ballpoint pen?
About 50 people.
Well, it could have been 50, but we talked different kinds. I took the pen and I broke it apart. Right? So we have the plastic case that it was in. There's a little soft thingy here, right? It makes it feel nice. Right? Here's a couple springs. Here is the ink cartridge, the little ballpoint pen thing on the end of it. If you push it down like this, right? The ballpoint thing comes out. If I put it in my pocket, I get ink all over my shirt. So I push it again, it goes back in. And what happens is, if I push this down, right, what it does is it rotates this thing, and there's some grooves in here, and it catches and holds it out. If I push it again, it rotates it again, and lets it pop back up, right? So that's what it looks like on the inside. It's got some ink in this cartridge, right? I took a look at this and I said, okay, here's the kinds of guys and girls that I would have to design my ballpoint pen. First of all, I would have a mechanical engineer, right? Some guy or girl, because there's a lot of girl engineers now, right, that design the mechanical part of this, right? A little gadget in there to where I can push the button down and the ballpoint thing comes out, right? Push it again and it goes back in, right? That's all mechanical. Okay, so I got to do a mechanical engineer. Then the next one is a chemical engineer. Probably need a couple different kinds of specialists in chemical engineer. One, I probably need a chemical engineer that's really an expert in plastics, because this is all plastic, all right? Part of it is hard, and that part there is what?
Soft.
Soft, right? Soft part, right? So there's a couple different kinds of, so actually about 3 different kinds of plastics in here. There's this part here, which is a little bit clear. There's this part, right, which is a different kind of plastic. There's this part, and then there's a plastic that holds the ink. So there's 1, 2, 3, 4 different kinds of plastics in there. So I need a chemical engineer that's really familiar with all the different plastics and their characteristics. Then I have, and I need another one, which is able to handle
The ink.
the ink. Right, ink is a very complex thing. Now, then I need a microbiologist.
What's that?
What's a microbiologist? Well, that's someone who is sort of like in the medical field, but what they do is they study little microbes, very small living things that we can't see. Why do I need one of those? Why do I need, for this pen, why do I need a microbiologist?
Because you don't want the pen to be really big.
I don't want it to be, well, yeah, I want it to be fit in my hand, but this person is going to discover, you know, is a scientist who works with these little small microbes, little small living things. Why would I need one of those? Is there anything living about this? I mean, it's sort of looks dead. I mean, there's some stuff on it because of I'm handling it, all right? There's goop on the outside. But. All right, I'll tell you. The reason is, you know the inkjet printers that you have now?
Yeah.
That spray the little ink out? The first people who used those, right, used them in typewriters, it was International Business Machine, IBM, right? And there's a really little tiny holes in there where that ink sprays out, right? And it sprays out and makes the pattern for all the different letters or whatever you happen to be printing. Well, worked fine, except their little ink cartridges very quickly stopped working. They were still full of ink, but they just stopped working. And they discovered that there were little living things growing in the ink. Even though they were so small we couldn't see them, what they did is they clogged up the little holes coming out of the cartridge, right? And once you clog up the little hole, then you no longer get these little droplets of ink coming out, right? So the same thing could happen here. If we get little things growing inside my ink, right, it could clog up the little area here where this little ball is rolling on the ballpoint pen, right, and the ink wouldn't come out. So what I need is this microbiologist, right, to make sure that I have something in that ink that's going to kill all those little living things so that they don't start growing and clog up my ink, right? The next one is a human factors guy, human factors engineer. You know what that is?
No.
All right, human factors is an engineer who studies how the human being is going to interact with this thing. Okay? And he's saying, well, you know, if the pen was this long, of course that wouldn't be too good to write with, right? It'd be a little difficult, so he's going to say, hey, you know, you need to adjust the length of the pen. And, you know, people, they don't, if it's this hard part up here, they're probably a little more comfortable, right, holding it, well, soft part. Take my pen, right? Which would you prefer to hold by?
This one.
That part, right? So the human factors guy probably is the one that decided how long this pen was going to be, maybe how much pressure you needed to put on the end of it, right? And human factors people are very important, especially if you get something more complex than this ballpoint, right? If you get into automobiles, who do you think decides where everything goes on a dashboard? Right? Why is the radio here and the speedometer here and the glove box over there and the steering wheel is able to tilt up and down? Who do you think decides all that? This human factors guy. Is an engineer, right? And that's all he does is he studies how people are going to interact with this thing. And it's the guided missile things, right? Like the Patriot system, right? The guys are in battle, right? And they're shooting down airplanes and things are happening fast and furious, right? So then it's really important because the human factors guy is going to say, okay, we're going to put the switch over here because this guy, when he gets panicked, right, and he needs to punch that button or flip that switch, right, it needs to be there. Same thing with airplanes. The airplane cockpit, right, is a lot more complicated than the automobile dashboard. So things have to be in the right place because if something happens, right, in the airplane, you need to be able to have that pilot and co-pilot act automatically, right? They don't have to, you don't want them to be looking around and thinking about, all right, where's the meter that I'm supposed to be looking? Where's the switch that I'm supposed to be? Where's the lever for putting the landing gear down in a hurry, right? It all needs to be controlled where it's at. So he's a very important guy, right? And then a production engineer. Our car that we designed, right? That wonderful car that does 100 miles a gallon, 100 miles an hour, and gets 50 miles a gallon. Right, we built one. We built a prototype. Right? But after you get the prototype built, you got to take that prototype, and the same people who designed this pen, they build a prototype to test. Right? Now then, it's got to go to manufacturing. Somebody's got to take and build thousands and thousands and thousands of these things. So the way we build it may not be easy to build in a production facility. So we need a production engineer on this team, right, to say, no, you know, rather than drill a hole here, maybe it's better to drill over there, and because it's easier for me to produce in the factory, to mass produce this thing. So you need that kind of guy. So my little simple ballpoint pen is going to have at least 5 different kinds of engineers working on it. Maybe even some more that I didn't think about, right? So Oh, so basically, the design process is a loop, it goes around and around. But first of all, we get step number one is to come up with the idea from somewhere, okay? And then we go down and we do some research. Then we go develop some solutions to that problem that we're trying to solve. We pick a good solution, we develop a prototype, and then we test that prototype. Then we communicate our solution to somebody, right? Either our boss or the customer, right? And then we go back, and out of that we have some redesign. We go around and around, and this can last like 100 years or so, as it did with the Oldsmobile. So that's the design process. Now, there's another sort of universal thing, and it's called Universal Systems Model. Okay, what's a model? What's a model?
Sample.
Huh?
A sample.
A sample. It's something that represents something, right? It's not, you know, anything else but that. It's a model. All right. And this Universal Systems Model applies to everything, basically. Right? The heating cooling system in here, right? The Universal Systems Model can apply to that. Because what we do, what happens? We go set the thermostat over on the wall somewhere, wherever it is in here, I don't know, right? And for a temperature that we want the room to stay at. Right? That sends a signal, a little electrical signal, to the heating and air conditioning system. It says, whoa, it's too hot, it's too cold, right? It causes the heating and air conditioning system to react. As soon as if it says it's too cold, the heating system goes on, warms up the air in the room. Thermostat says, whoa, now it's up to 70 degrees, whatever we set it for, and it shuts the heat off. If it gets too warm in here, right? Say we had the thermostat set for 70, and the temperature gets up to 75. It says, well, sends a signal over to the heating and cooling system. Says, turn the air conditioner on and cool the air down. As soon as the air gets back down to where we had it set at 70 degrees, it shuts it off again. So that kind of system, universal system model, right, applies to that. And what it basically is we have a input or a goal. In the case of the air conditioning heating system, is to keep the room temperature the same, which gives us an input. There is a little processor, a little computer kind of a thing that analyzes what we're doing, and it gives us the output. It either turns the heat on or turns the air conditioner on. Right? Then through the air coming back to the thermostat, we have what's called a feedback system. It comes back and says, okay, in the case of the air conditioning heating system, if the temperature is right now, stop, right? Don't shut everything down and wait to see what happens to the temperature. As soon as the temperature changes, right, our input changes again, and we start everything all over again. So that's a universal systems model that we're talking about. And it applies to everything. All of our activities. We get in the car, start driving the car down the street. Now then what we want to do is, I'm going to give you a little test. Just to demonstrate this. We're going to put up some little pylons. I'm going to take that one and fold it up too, like this. All right, Melissa, you're going to take the car. Now here's your goal. What I want you to do is I want you to start your car out here, and I want you to drive it around over till you get to the blue one, go around the pylons, right? And I want you to stop at the blue one. All right, pretty easy.
Yeah.
Okay. And what we did is I give you a goal, and you started an input by pushing the car, right? And when you started to push the car over here, when you started pushing the car, you said, okay, now then you're watching it, and what happened? You said to yourself,
You have to turn.
you have to turn, right? Because it's going in the wrong direction. So you made it turn, right? You got over here and you said what?
Have to turn again.
Have to turn again. Now where's the feedback, right? the input is we're pushing and we had a goal, right? But what was the feedback? The feedback was the one that says, okay, you got to make a turn. And what told you that I needed to make a turn?
You have to go.
You were watching it, right? You're watching it. And I moved over here and you said, okay, it's far enough. Your brain says, because your eyes are watching it, says make a turn, right? You got over here and what happened?
You have to make a turn.
And I have to make a turn. And how did you know that, Catherine? Because you're
Yeah.
watching it, right? So the feedback is through your eyes, your brain, and back down to the muscles which are controlling the car. All right, now Melissa, what I want you to do is to close your eyes, no cheating, and see if you can drive the car through the pylons. Right, how did she do?
Very bad.
Yeah, very bad. Do you think you could do better?
Yeah.
You think you could do better? All right, why did you do very bad? The first time you went through and when you were able to see it, right, you went right through, no problem. Now then we make you close your eyes and what did we do?
Because my brain can't send a message to my.
Your brain
Yeah.
can't say, we took the feedback loop out, right? We took this feedback, right? This feedback loop here, we took out, right? And all we did is you got an input that says, go drive through the pylons and get to the blue one, right? So your muscles said, your brain says, okay, let's start, boom, you had an input, right? It processed it and you went around and around and around, but you had no feedback. You didn't know whether when you were going right, you were going in the right direction, or when you were going left, you were going in the right direction, and so forth. So when you lose that feedback loop, you're not able to proceed too well. Same thing. Last summer we launched Sprint satellite rover to Mars. Just think of the problem that they have. Right? Now, what I want to illustrate that problem, what I want to do is we take. Melissa, you take the car again, and you close your eyes. Catherine, I want you to tell her, we're going to use your eyes to tell her which way to turn.
Okay. Turn. Not that much. Okay. Not there. Turn. Okay, turn.
All right, did she do much better?
A little bit.
No, really, she run over everything, all right? So she really didn't do much better. What was the problem? We had a feedback loop, but what was the problem with our feedback loop?
She couldn't see it.
She couldn't see it, but you could see it for her, and you were telling her, right? You're telling her to make a turn. But what was happening?
She didn't have a feedback.
Well, yes, she
I didn't
did.
have
You
my
were
own.
part of the feedback loop this time. But what was the problem? Why did she keep running over things? You told her to turn, right? But then, did she turn immediately? Really? Instantly like that?
No.
No, it took a second or so for her to make the motion, right? And then if she turned too far, right, and you saw that she turned too far, you had to say, whoa, wait a minute, stop, you turned too far, don't turn quite so far, right? But it took a little time, right? So there was a delay in the time when the turn was made, right? And if it was the wrong turn, there was a delay in getting the information back over here to the input. Now, the Mars rovers that we just sent up, right? The guys down at NASA are telling them, okay, I want you to go forward 100 yards, stop. Right? How long do you think it takes for that message to get? It's radio signals travel 186,000 miles per second. Right? How long do you think it takes for it to get to Mars?
About 20 minutes.
Well, it's 20 minutes round trip. It takes 10 for it to get there. It takes 10 minutes for it to get up there. Right? So the guys down at NASA say, okay, we want it to go 100 yards, and we send the signal now. 10 minutes later, it gets to the vehicle up there, the little Mars rover. The little Mars rover starts going off. Now, if something happens, it takes 10 minutes for it to get back to NASA to tell them, whoa, you know, something happened. So our feedback, right, the delay here is really about 20 minutes, right? 10 minutes up, 10 minutes back. We put a signal in, tell the rover to do something, right? And we don't know for 20 minutes whether it's done what we want it to do, right? And so in the meantime, that 20-minute period of time, the little rover is moving along. It was told it to go 100 yards in that direction, so it's moving along, right? And it comes up to a big hole in the ground, and it goes bloop down in the hole. And we just lost a rover, right? And it takes us another 10 minutes to find out that we've lost it, right? So what we have to do in that case is we have, in this processor here, right? This is done by a computer on the Mars rover. We got to put some smarts into it. Okay? We got to make it sort of intelligent. So if we tell it to go 100 yards, and it comes to, it recognizes that, hey, it's going to run off a cliff and fall in this big hole, it stops. It says, "Whoa, hold it." You got to send a message back to headquarters down at NASA that I got a hole in front of me. Right? So it sends the message back, says, "I got this big hole. You don't want me to drive in this big hole, do you?" And the guys down there said, "No, that wouldn't be good. We just lost a couple $100 million." Right? So then they send another message back to make a correction. Right? So there's got to be some intelligence. If this loop gets too long, it takes too much time for the feedback, then things don't work quite right. But this universal systems model works for you driving the car through the pylons. It works for the Mars rovers. It works for our heating and cooling system in here. Right? All those things, that universal model can be applied to everything. Now, if we take, I have a question for you. The question is, we have an automobile, right? And which of these following things are part of the feedback system? The steering wheel, is that part of the feedback?
No.
Hmm?
No.
No. Well, she's saying yes and you're saying no.
I say no.
Why? Why did you say no?
Because
It's the input, right?
yeah, you
It's part of the
control it.
input, right? It's what you would use if that was a real car to drive around those pylons to get to the end of the course. So that is part of the input. The next one, the brakes.
No.
No, that's also part of the input, right? If you get to going too fast and you think you're going to run over the next pylon, what do? You put the brakes on, slow down a little bit, right? The speedometer.
Yes.
Yeah, both of you agree on the speedometer. Why?
Because it tells you how fast you're going.
It tells you how fast you're going. If you're driving not going down the pylons, but you're driving down Interstate 93, right, and your speedometer says 80 mile an hour, what's your brain tell you?
Slow down.
Slow down, all right? So that's a feedback loop that says slow down, right? Because if I don't get back down to 65, there's probably going to be a cop giving me a ticket, right? So, besides, it's too fast to be driving anyway, and it's dangerous to slow down a little bit. And the accelerator pedal,
No.
that's another input, right? So in this test question, we have 3 inputs. We have the steering wheel, the brake, and the accelerator, and the speedometer is part of the feedback. Would there be any other feedbacks? I mean, is that the only thing? When you're driving a car, is that the only part that's important? Is it the speedometer?
No.
No.
Hmm?
No.
What else do you think might be a feedback, part of the feedback loop? A lot of things that you don't even think about, that you do automatically, right? If you're driving a car and you're going around a corner and you go around too fast, what happens? The car might tip over, right? But what happens to you in the seat when you go around the corner? Let's say I'm driving and I go around, make a right turn, right? What happens to me when the car starts to make the turn? What happens to you if you're sitting in the back seat and I make a right
You
turn?
turn.
You sort of fall over, right? Right, because your body wants to go straight, right? And the car is going around, so your body tends to good old Newton's laws, right? The ones we can't break, right? Says your body wants to go forward. So what you do is your body comes up against the side of the thing. Well, right, a lot of people, especially experienced drivers, right, instead of looking at the speedometer constantly, respond to those motions in the car. When the car accelerates, when it brakes, slows down, right? Brakes, slows down, you go forward. When it accelerates, you go back in the back of the seat. So you adjust your speed based on those kinds of things. Right? You know that if you're going to make a real hard turn to the right, just your brain knows. Right? You may not be thinking about it consciously, but your brain knows. If you're making too hard of a turn to the right, and you're really rammed up against the door, probably there's a good chance that the car might tip over because it's going around a turn too fast. So all those things. Anything else you might think about? This might be an indicator. It be a feedback thing. What if you're driving on the road, nice and straight, okay? And all of a sudden, in front of you, car stops. What are you going to do?
Slow down.
Stop.
You're either going to slow down, stop, or go around him, right? And what's the feedback there?
To move.
Same feedback as you had here, right? You were watching what's going on, right? As you're turning this around, okay? So you know where to go. Well, you're part of the feedback. You're the human person in this automobile is part of the feedback system. So you're looking out, and the sensor that you have, you're looking out through the windshield, you see a car stop, right? The little red tail lights go on, and it slows down all of a sudden. So it comes back, and you either step on the brakes, right? Turn the steering wheel, one of those things, so that you can avoid running into the back of the car, hopefully. Right, so that universal systems model that we have applies to all kinds of things, right? It starts out, we have a goal, something we want to do, ride a bicycle down the street, drive a car down the road, drive the car around the pylons, put a rover on the moon and have it go explore things, right? And we give it some sort of input to make it start doing that. We have some sort of a process that makes it move, right? And we get an output, which is the result, right? Then we have some sort of a feedback to control it, because it needs to know when it gets to where it's going, this happens. So that feedback loop in here tells us what kind of corrections to make, really, right? Whether to speed up, slow down, in the case of a car, turn left, turn right, whatever. If this feedback loop gets to be too long, takes too much time for the feedback to happen, what happens? The system doesn't work quite as well, right? If this gets too long. So, the other thing that we talked about a little bit was the design process, engineering design process, which had how many steps?
8.
Had 8, right? Had 8 steps, and we start out by identifying the problem, right? Studying the problem, come to do some research to find out what's happening, develop some solutions, right? Then like we did with the cars, right? We between us, our little engineering team, we decided what we were going to do, what kind of car we were going to build, right? So we selected the best possible solution, and then we constructed a prototype, which is, prototype is what?
Sample.
It's a sample, it's a model, right? And usually it's a full-size working model, right? And then we tested it, right? Because we may have made a mistake when we did some design, right? So we need to test it a little bit, right? In some cases, quite a bit, right? Then we need to communicate to our boss what a good design it was, and he possibly comes back and says, no, right? Can't do that, right? We need to do a redesign, and we start the process all over again. And how long does that last?
Here.
It could be a long time. It could be a very short period of time, but usually it's pretty long. And that's the case we pointed out with our Oldsmobile, which they just quit building last week, right, after 106 years. That car has been redesigned and redesigned So that coming from something that looks like an old horse and buggy kind of a thing, right? Even though it still had 4 wheels, it had headlights, right? It had a little tiller here to steer it with. It had air conditioning because there was no windows on it, right? And you're driving down the road, the wind was blowing across you, so it had air conditioning. It didn't have any windshield wipers, right? Because it didn't have a windshield. But anyway, that was design that over 106 years changed into a modern automobile. One of the things that I like about this picture, right, this 1908 Oldsmobile was an electric car, right? What are we trying to do today? We're trying to build an electric car, right, because of the pollution. Well, this one, 1908, how many years ago that was, right, was an electric car. The other funny part about this particular picture is, you know what this thing is right here?
What?
I know you weren't around in 1908, so you wouldn't recognize that. But this is an electric car, and this was an old gas pump for gasoline, sitting right beside this electric car, and I think that's sort of funny. So that's it for today. Just remember, we have two universal things. One is the engineering design concept, and the other is the universal systems model, which both of those models apply to almost everything that we have around us today.